So we have talked about equilibrium, what that means, and also the mathematical expression of it, which is called the reaction quotient. So the reaction quotient, we call it QC, and if you remember, it actually looks a lot like this right here. So QC, the reaction quotient at equilibrium, so specifically at equilibrium, we call it Kc, so the equilibrium constant. And the overall calculation of it is exactly in the same way as the reaction quotient. It's just specifically the concentrations that you will plug in here are the ones at equilibrium. And then one thing I do want to know is to not confuse this with the kinetic rate constant of little k. This is a big K, a capital K with a subscript of C. So in this example, we will be evaluating a reaction quotient and also actually a equilibrium constant. So we will be determining an equilibrium constant. So in this problem, we have gaseous nitrogen dioxide forming dinitrogen tetroxide. It's actually that same reaction we were looking at earlier. It's just flipped around. So remember, these are reversible reactions, so you could start either way. In this particular reaction, we are starting off with NO2. We have 0.1 mole of NO2 being added to a 1 liter flask at 25 degrees C. The concentration changes so that at equilibrium, so pay attention to that wording, at equilibrium, we know that the concentration of NO2 is this, 0.016 molar. The concentration of N2O4 is 0.042 molar. A, what is the value of the reaction quotient before any reaction occurs? B, what is the value of the equilibrium constant? So part A is asking for a reaction quotient before the reaction occurs, so at time 0. And in order to solve this, we first have to pick out what information means what. So in yellow, I'm going to highlight what is relevant to A. So if we read this problem again, when 0.1 mole of NO2 is added to a 1 liter flask, that's telling you, okay, I'm literally taking 1 mole of this NO2 gas and I'm adding it into this 1 liter flask. So this is what you're starting off with at the very, very beginning before the reaction even occurs. And then for the other, for B, I'll highlight in green. So B, it'll be green. And then the problem tells you at equilibrium, we have NO2 this, and N2O4 is equal to that. So here we have information for both of these problems. It's just a little bit not hidden, but you kind of have to pick it out. So that's part of learning how to solve these problems, is being able to differentiate what information refers to what. So for A, we are going to calculate QC equals, and first we have to set up this reaction quotient according to this reaction. So remember, it's products over reactants, NO2, and then we raise it to the coefficient, which is 2. Okay, so we have to find the concentration for NO2 and also for N2O4. So the concentration for N2O4, and this one is going to be easy, it just requires you to think about what's going on just yet. So before the reaction even occurs, you only start off with this reactant. You don't have any product that has formed yet if the reaction hasn't occurred, right? It's telling you before the reaction occurs. So before the reaction starts, you never have any product. So we have 0 molar. For the reactant, they told us that, and we're going to have to calculate this, that we had 1.1 mole in 1 liter. And if you remember, molarity equals mole per liter. So we're going to divide that 0.10 mole divided by 1 liter. And luckily that's an easy calculation. So it's 0.1 molar for our NO2. So now that we have everything, we can go ahead and plug everything in. So so you can see that it's a 0. So our reaction quotient will equal 0 molar divided by 0.1 molar squared. And you know, obviously anything of 0 divided by whatever number, we don't even have to go through with the calculation. It's going to equal to 0. So our reaction quotient in this case is 0 for A, QC. So that's A. Now what about B? So in a very similar way, we're going to figure out what we need to plug in. So KC is calculated in the exact same way that we calculated this up here, except it has to do with concentrations at equilibrium. So the overall setup is the same. The only thing is that the concentrations are different. And remember, what's highlighted in green is what we will be using. So for N2O4, we know that the concentration at equilibrium is 0.042 molar. For the NO2, the concentration at equilibrium is 0.016. And all I'm doing is just rewriting them so we have them. Now let's actually plug in. So Kc equals our 0.042 molar. And then for NO2, it's 0.016 molar squared. One thing about both Kc and QC is that they are unitless. So they do not have a unit. So don't worry about units here. So we are going to take our 0.042 and then we're going to square that bottom part, the 0.016. When you divide this out, you will get 1.6 times 10 to the 2. So our equilibrium constant is 1.6 times 10 to the 2, post Kc. So those are both answers, that one and this one up here. So here let's just quickly recap and compare Q and K. So both of them are calculated the same way. So the major difference between them is that K, the concentrations must be at equilibrium. For Q, the concentrations do not have to be at equilibrium. It can be at any point in time in the reaction. And then again, this is what I stated earlier, Q and K are both unitless, they don't have units. And then something else to point out is that the value of the equilibrium constant is dependent on temperature. And the reason for that is because with molarity, you have moles per liter, which is a volume. Volume is dependent on temperature. If temperature changes, volume changes. So that's something to note. Another thing to note is that the value of the equilibrium constant is independent of the starting amounts of reactants and product. So let's say you have this reaction, and let's say you have two situations. This is, you know, let's just call this 1 and 2. In situation 1, you're starting off actually with your reactants. So you have SO2 and O2 high, right? And then SO3 is what's being formed. So we are starting off with a bunch of reactant on this side. After a certain point, they will reach equilibrium. You see that equilibrium is right here, and the concentrations for both the reactants and the product, the SO3 product, they are a certain value and they stay at that particular concentration. And you know, you will have a certain value for that equilibrium, right? So you will have a certain Kc, a equilibrium constant attributed to those conditions that you started off with reactants. Now let's look at situation 2. In situation 2, you're actually starting off with your product. So you see how you have a high amount of product and you have no reactant just yet. So in that case, you started off on this side and you're going towards the reactants. But either way, when you reach equilibrium, those concentrations are the same as what we looked at earlier. So those equilibrium concentrations, regardless of whether you started with a bunch of reactant and you're going towards the product, or if you started with a bunch of product and then you were making the reactant, so you were going reverse, it doesn't matter. Those concentrations stay the same. So does the equilibrium constant. So the equilibrium constant, again, is independent of how much you start off with of reactant and product. So how can we compare K to Q. So in order to do that, let's first talk about K. So if K is very large, the mixture contains mostly products at equilibrium. So how does this happen? Why is K very large, and how do we know that it's mostly products? So if we go back to the definition of it, it's products over reactants, right? So I'm just going to write products, react for reactants. Oh, I spelled that wrong. Well, you get the point. So it's products over reactants. And if you have a large number right here divided by a smaller number of reactants, you're going to get a large number overall when you divide this out. So that's why a large Kc means that you have a lot of product, versus the opposite. If you have a very small number of products divided by, your reactants, this is going to give you a small k. So what this means is that you had more reactants than products. So that means that your equilibrium lies to the left, versus whenever you have a very large K, your equilibrium lies to the right, meaning that the products are favored and they are produced more. Now, again, the value of K has nothing to do whether the reaction is fast or slow. The rates, the only thing that ties the rates to the equilibrium is the fact that the rate forward is equal to the rate backward. But it's not telling you, okay, is this reaction happening fast? That's not what the equilibrium constant is telling you. So anytime a system is not at equilibrium, what will happen is that the equilibrium will want to be established. Nature likes equilibrium. So the direction that establishes equilibrium is where the reaction will go towards. So we can compare Q to K, and then we can determine which direction the system will take in order to achieve that equilibrium. And basically these are our directions. So when Q is less than K, the forward reaction will be favored. When Q is greater than K, the reverse reaction will be favored. When Q is equal to K, the reaction is at equilibrium, so the concentrations will not change. So here in this example, we will be predicting the direction of a reaction. So overall, our goal is to compare Q to K. So we want to be able to get both of these values so that we can compare the two and determine, is it bigger than K? Is it smaller than K? Is it bigger than K? Is it equal to K? So we need to determine those things. So in these problems, we're going to calculate the reaction quotient and then determine the direction. Notice that in both of these, and I'm actually only going to do B because I did A in the problem solving session. So if you want to see how we solve that, go to that recording. But for B, notice that we are given the equilibrium constant. So we have K. What we need to calculate is QC. So in a 5-liter flask containing 17 grams of ammonia and 14 grams of nitrogen and 12 grams of hydrogen, we need to find this reaction quotient. So QC is equal to the products of the reactants. So this part is probably, easy peasy. The concentration, and then we raise it to the power, and then we divide by the reactants. So N2 H2 raised to 3. Now, normally all we would have to do is fill in the concentrations, like if it was an easier problem, but notice that we are given grams, and liters. So what we have to do is find the concentration of each of these. So we have to find the molarity of all of these. So I'm actually going to zoom out a little bit to find the molarities. So first, to find the molarity of NH3, we need to find mole and then divide that by our liters. So to find mole, so we're going to do this for each of them. First, we need the molar mass of NH3. The molar mass of NH3 for N it's 14 grams per mole, and then for hydrogen it's each about 1 gram per mole. So I'm gonna, keep it simple. That adds up to 17 grams NH3 is 1 mole NH3. So overall this gives us 1 mole of NH3. And then in order to get molarity, we would divide this out by liters. So here we have 5 liters. So this would give us 0.2 molar NH3. And then we're going to do the same thing for the rest of these. So again, I'm going to zoom out. For our N2, we have 14 grams N2. The molar mass of N2 is about 28 per 1 mole. This gives us about 0.5 mole N2 divided by 5 liters. Now from here, you should get 0.1 molar N2. And then finally, for H2, we have 12 grams. The molar mass of H2 is about 2 grams. So you get 6 mole of H2. Divide this by the 5 liters, and then we get 1.2 molar H2. So now we have the concentrations of all of these, and now we can go ahead and plug in to what we originally started off over here. So I'm going to write a little bit bigger, but basically it would be our 0.2 molar squared divided by our N2, which is 0.1 molar, multiply that by 1.2 molar cubed, and then you plug all this into your calculator. You should end up getting 0.23 as our QC. So this is what our QC equals right here. Okay, so now let's go back. So we know that QC equals 0.23. We also know that our K, and it's right here, is equal to 0.060. So right off the bat, so we don't really need our number line here because it's not a big number or a small number, so it won't really get us confused. We can obviously see that K and Q, between these two, that Q is bigger, right? We can see that 0.23 is bigger than 0.06. So here the situation that we are looking at is that Q is greater than K. So what that tells us is that the reverse reaction will be favored. So here the answer to B, we have both the the reaction quotient we calculated, as well as we determined what the favored shifting of equilibrium will be. We know that the reverse reaction will be favored.